Great. Thank you for joining us today. My name is Ashley Eldridge. I'm with EPRI. I want to go over a few housekeeping items before we get started. Your lines are all muted. Please keep your lines muted so we can hear our presenters nice and clearly. We are expecting a good number of attendees, so that's why we chose mute upon entry. If you have any technical difficulties throughout the call, please send a chat message to me. My name is Ashley Eldridge. You will find me in the participant list, and I will go ahead and assist you offline. Today, we're going to have a CIGRE Next Generation Network webinar on grid regulatory modernization and the utility of the future. We're going to have two presenters today. Our first presenter is going to be Dr. Julio Romero. He is the Vice President of Strategy and Business Innovation at Quanta Technologies. And our second presenter is going to be Dr. Saeed Kamalina. He is an Assistant Manager in Consulting the Analytical Services Department of S&C Electric Company. He's also the Executive Committee member and Chair Professional Development Committee at CIGRE USNC Next Generation Network. At the end of the webinar, Saeed will be introducing the CIGRE NGN activities and structure, and he'll be moderating the Q&A section. Throughout the presentation, please send questions and comments via chat to Dr. Kamalina, and we will go over them at the end of the presentation. With that, I'd like to hand the call over to Dr. Julio Romero. Julio, the floor is yours.
Oh, thank you, Ashley. Thank you for the introduction. Good afternoon or good morning, everyone, depending on where you are. It's a pleasure to be here. My name is Julio Romero Agüero. I'm Vice President of Strategy and Business Innovation at Quanta Technology. Quanta Technology is a technical consulting firm. We provide advisory and technical consulting services to electric transmission and distribution organizations. So it's a pleasure to be here. The topic of this presentation is grid and regulatory modernization and the utility of the future. These are certainly vast topics, and we can talk probably for hours about them. So what I'm going to try to do today is to highlight a few aspects, a few key topics that I believe that are important. And basically what we would like to do is to encourage discussion in the industry. These topics certainly are being discussed already, but I think my personal opinion is that we require a holistic approach. We need to look at not only grid modernization, we need to look also at the regulatory and business side in order to outline a successful transition into the utility of the future. So that's the main topic of this presentation. So let me start by introducing a few topics, a few terms that you may have heard about them before. Well, grid modernization, certainly that's a very hot topic these days in the industry. It's basically a hands-on, comprehensive portfolio of initiatives that have the purpose of realizing the smart grid or the grid of the future vision. So basically, is the realized or field implementation of that smart grid vision or grid of the future vision. And it consists mainly on the deployment of incremental grid intelligence. Let's remember the grid is already intelligent, especially the transmission grid. So what we are trying to do is to increase the intelligence of that grid by via the utilization of smart technologies. But besides that, we also need to look at foundational infrastructure. We also need to look at IT and OT infrastructure, and also at engineering processes. So generally, when we talk about grid modernization, we are considering all of these aspects. Now, what is utility of the future? Utility of the future is also a term that is being used frequently. Generally, it's considered a long-term utility vision that is adapted to a projected business environment. Now, grid modernization focuses on the grid itself and related aspects. Utility of the future goes beyond that. It includes also business, regulatory, customer aspects. And then something that is perhaps not discussed too frequently, I would say, in engineering circles is regulatory modernization. And the key point here is that we can make significant investments in modernizing the grid and making the grid more intelligent, in being able to monitor and control in real time, and do many interesting and advanced engineering analysis. But if we don't pay attention to the regulatory and business side, then probably our initiatives are not going to be as successful as they could be. So basically, regulatory modernization focused on the required changes to existing regulatory frameworks to enable that vision, that utility of the future vision, and to allow customers to take full advantage of the opportunities derived from grid modernization. Why is utility of the future important? Why are all these topics important, grid modernization and so on? Basically because the industry is changing, the electric grid is changing, and there are many drivers behind that change. Perhaps the key driver that we have seen emerge in the last decade specifically is the proliferation of distributed energy resources, and specifically distributed generation. That is changing, it's a new paradigm that is changing the way not only distribution systems, in general, transmission and distribution systems are being planned, operated, engineered, designed, and so on. So that's perhaps the key driver, but there are others. Basically, another that is very important is the evolving consumption patterns or expectations from customers. When we compare customer patterns and customer expectations today versus those of, let's see, the early 90s or early 80s, there is a significant difference. One of those key differences is perhaps the expectation from customers of being supplied using sustainable technologies. Besides that, technological advances in computational systems are today allowing us to do analysis to collect and process data, things that we couldn't do 20 or 30 years ago. So that's another key driver or enabler for these changes. But the point here is that in this evolving environment, there is a need for new business models. Not only, we don't have to focus only on modernizing the grid. There is a need also for new business models and for new regulatory frameworks. This is a summary of some of those key trends that I mentioned before. DR integration, certainly, that's one of those key trends. If we want to be a little bit more specific, new technologies such as smart inverters, new concepts such as microgrids, the emergence of energy storage, the proliferation of distributed generation, certainly. Then we also have business models. A good example could be the Reforming the Energy Vision initiative in New York. The ongoing discussions regarding rates unbundling, specifically the introduction of demand charges in some of the states here in the U.S., the interest from utilities in service diversification, going beyond providing kilowatt-hour sales, getting into other aspects. In the same way that telecommunications and cable companies diversify their services in the last 10, 20 years. So utilities are interested in doing something similar. Transactive energy, it's another one of those emerging trends. OT-IT convergence, certainly that's a key trend. The interest in being able to increase awareness especially over the distribution grid, but also the transmission grid. The emergence of grid analytics, increased visualization, operation in real time, operation in control, monitoring and control, automation in real time. The introduction of systems such as advanced DMS, DERMS, or advanced distribution automation, advanced sensors, AMI, etc. Another key one is reliability and resiliency. Regarding expectations of customers, when we consider reliability and especially resiliency, there are growing expectations from customers. Now, resiliency covers several different aspects. something that is emerging as a key trend, a key need for utilities is cybersecurity. Since we are integrating a large number of intelligent electronic devices, those can become vulnerability points for the IT system of a utility. Besides that, we have aging infrastructure aspects that need to be addressed. And then there are new concepts like smart cities, in the same way that the smart grid has been introduced in the electric power system. Other services providers of critical services such as water or transportation, they are introducing similar initiatives in their respective fields. So basically, smart grid, the smart cities, that concept calls for utilization, sharing data, sharing resources, utilization of data to improve the livability, the workability, and sustainability of cities. So that's another important trend. Now, I mentioned that the proliferation of distributed generation and the proliferation, well, the utilization of sustainable resources for power production those are perhaps two of the key trends. Now, what is behind that? Certainly societal concerns regarding climate change, and due to those societal concerns in different states, specifically here in the U.S., regulators have introduced renewable portfolio standards, and basically what they call for these renewable portfolio standards require electric utilities to produce or to procure a percentage of the electricity that they sell to end users via renewable resources. So some of these renewable portfolio standards are quite aggressive, but the important point here is that it's a trend that is being observed all over the U.S., and if we go overseas, if we talk to colleagues in Europe, in South America, Asia, and so on, it's a trend that is being observed all over the world. Now, I mentioned DER integration as a key driver, and something important is to highlight that this is a reality. This is something that is already happening in many utility systems. This is a good example. This is the island of Oahu in Hawaii. This is publicly available information. I have provided the link if you would like to review these maps. They are available online. They are called locational value maps, and basically the electric utility responsible for the island of Oahu, Hawaiian Electric, what they do is they publish this information on a daily basis. They update it, and what we see here is for the feeders, distribution feeders in their service territory, they are providing an estimate of the DG penetration levels in their system, the distributed generation penetration levels in their system. And you can see that in some of their feeders, those penetration levels are quite high, above 100% or above 250%, which is significant. Of course, the penetration levels of distributed generation are going to depend on several different factors, the type of incentives that are being offered to developers or to end users in each state, electricity prices in each state, and so on. But the expectation, one of the expectations is that as technology prices decrease, and that is a trend that is being observed, the proliferation of DER may occur in other utility systems. This is also from Hawaiian Electric. This is information updated to September 21st, so basically yesterday. So in this renewable watch plot, well, Hawaiian Electric also provides this information to the general public. Basically, by comparing those two plots, you can see a blue line and also a light blue line. Those what we have here is a comparison of the demand being supplied by Hawaiian Electric and the total demand that is interconnected to their system. Part of that demand is being supplied by behind-the-meter resources. So you can see that in this specific case, there are some hours of the day when over 100 megawatts of demand are being supplied by behind-the-meter resources. In many cases, this is photovoltaic distributed generation. So as I mentioned before, this is a reality. This is something that is happening already. This is from California ISO. So in the California ISO system, they do the same. They compare the total load in their system, and also the total load once we subtract what is being supplied by renewable technologies, in this case wind and solar. So you can see that there is a significant proliferation of wind and solar in this utility system. So the question is, are we heading in this direction? This is Germany. This is data from last year in Germany. This is specifically for 15th of April of 2015 at 1:15 p.m. Local time. So you can see that at that time, the total generation, solar generation, photovoltaic in this case, in Germany, reached about 27.5 gigawatts, which is impressive. So especially in a system, the German system, of course, is smaller than the U.S. So in a system such as Germany, that amount of generation being supplied by photovoltaics is certainly significant. I mentioned before that technology prices are decreasing. So one of the expectations is that at some point we're going to reach what is called a grid parity. When that happens, basically, if I am an end user, and if in the area where I live, we already achieved grid parity, when I compare the prices of electricity prices, a comparison between being interconnected to the utility grid versus installing my own distributed resources and self-supplying, when I make that comparison, then I realize that at least from the point of view of electricity price, it makes sense. It's a good deal, let's call it that way, to self-supply. So the expectation, there are several different studies. Some studies are very conservative, other studies are very optimistic. The point here is, regardless of the study, all of them agree on one point, that it will happen. We are going to reach grid parity sooner or later, probably in the next decade. Some of the conservative studies indicate that it may happen in 15 years. Some of the more optimistic studies says, well, it's going to happen in the next 5 years. I think that the truth is somewhere in between, but the point here is that if technology prices, PV prices, for instance, continue decreasing at the same pace, based on the historical information that we have, we are going to reach grid parity most likely in the next decade in many markets here in the U.S. There are some markets where this already happened. And this is historical data, some of the historical data that I mentioned before. So you can see this is historical data for the last, let's see, this is from 1998 all the way to 2015. So you can see how PV prices for residential PV installations have decreased steadily. And this is happening despite the fact that state and utility incentives are decreasing as well. So that's what you can see in the second plot. You can see how rebates and incentives in general are decreasing. So the point being here that, well, reaching grid parity is only a matter of time. And when that happens, then, well, that can open the door to additional challenges for electric utility systems. Now, I was talking about PVs, but the same trend is being observed with batteries. So you can see in this plot also how technology prices of grid batteries, grid scale batteries are decreasing. And besides that, there are several new initiatives, ongoing initiatives in the U.S. that are one way or another incentivizing further decrease in prices. So to give an example, there is an important initiative ongoing right now in California. The CPUC, the Regulatory Commission, requested the 3 IOUs in California to deploy energy storage in the next few years. So that's a good example in the order exceeding 1 gigawatt of installed capacity. So that's a significant boost for that industry, and that may lead to further decrease in technology prices. Okay, so what happens once, let's suppose that we reach grid parity, and so at that point it is attractive from an economic standpoint. It is attractive for an end user to self-supply. And let's suppose that happens through not only photovoltaics, it can be another generating technology, and probably even batteries have reached grid parity. So when that happens, self-supplying is feasible. So a potential scenario is what is called grid or load defection. Grid defection would be an end user disconnecting completely from the grid. In the same way that in the telecommunications industry, many end users decided to disconnect from landlines and move into cell phones. So that would be a potential analogy. So grid defection would be disconnecting completely from the grid, having self-supply, distributed resources, and being able to cover all the demand. Another potential scenario would be load defection. Load defection, what it means is, well, I'm still connected to the grid, but most of my load is being supplied by my own distributed resources. So I'm still a utility customer, but I barely use the utility. Basically, I use it as a backup. So that's another potential scenario. In either one of these scenarios, and also under the assumption that the utility model is based on kilowatt-hour sales, what this may lead to is to a scenario where electricity rates might increase. So if that happens, if electricity rates increase, then customers may assess if it's convenient or not being interconnected to the grid, and that may lead to additional grid defection or load defection. So that's what is called, and you may have heard this term before, utility death spiral. So that's kind of a nightmare scenario. Now, is it going to happen? Well, it's a matter of debate. It's the point being here is that reaching grid parity and the potential grid and load defection may introduce business challenges for utilities, and it's important to prevent and to prepare to address those business challenges. So some of the initiatives that I mentioned before, like diversification, for instance, it is being motivated to a certain extent by this concern. Okay, now, since we are talking about the business side and the regulatory side, there are new concepts being introduced, new business models and new potential scenarios. One of those is what is called the DSO model, basically distribution system operator here in the U.S. And basically the idea here is, well, since now we are going to have distributed resources in the distribution grid, well, I could create a market in distribution, a market that is analogous to the market that we have in bulk power systems. So basically in that market, we would have merchant distributed generators, we would have end users, we would have prosumers, end users with the ability to either produce or consume electricity. We may have microgrids, and we would be able, these customers and these entities would be able to engage in physical and financial transactions in the same way that we do it currently we do it in bulk power systems. So a potential scenario, potential business model is electric utilities evolve and become administrators of that electricity market. So they either operate the grid or operate the market, or potentially do both. If both functions are being considered, then there may be a need to introduce a firewall between those two functions to prevent market manipulation, and so on. So that's a potential scenario that is being considered, being proposed by some researchers and colleagues that are experts in this field. One of the interesting initiatives that is somewhat, well, I mentioned the Reforming the Energy Vision initiative in New York, and they are discussing a model that is called the Distribution System Platform, the DSP. And in that vision, an important concept here is considering distributed resources within the portfolio of projects used by utilities for planning the expansion of the grid. So basically, in the same way that right now in most utility systems, when we need to expand the grid, when we need to supply new loads, we may build new substations, we may build new lines. One of the considerations under the DSP is to, well, let's also consider the possibility of using distributed resources to address those needs. Okay, so in general, let's try to summarize what the industry is doing. At the beginning, I would say in the last 10 years, 15 years, especially the last 10 years, at the beginning of this new trend, the proliferation of distributed resources, the key interest was on technical aspects, okay? How do we integrate these resources in a seamless manner? How do we mitigate potential problems? How do we reinforce the grid so there are no there are no impacts on operations or planning and so on? So that is still a concern, but I think that utilities have moved or are moving beyond that concern. That is becoming standard business, I would say. Basically, the realization that, well, distributed resources are an intrinsic component of modern and future systems, T&D systems. I think that we are reaching an agreement about that. So now the concern is moving into business processes, into infrastructure, information systems, into regulatory and policy aspects. So that's the trend these days. Now that we have this new reality, how is it going to affect our business processes, our business practices? How is this going to affect what we do on a daily basis or on an annual basis? Things like, if we move into the planning side for a moment, things like load forecasting, how distributed resources are going to affect load forecasting. How should I do load forecasting in this new reality? The business models that I mentioned, that I presented before, are a good example of, okay, how distributed resources are going to affect utility revenues. Should we diversify? Should we do more than 7 kilowatt hours? Should we provide other services? Should we install distributed resources, maintain and operate distributed resources, and help customers participate in market activities? That's a potential application. So utilities are working on actively in this area, and we believe that this is going to be an area with plenty of activity in the next decade. These are some examples of what utilities are doing, and this is specifically in the case of California. So something that I mentioned before, this is very similar to what Hawaiian Electric is doing in Oahu. Basically, the IOUs in California are publishing, let's see, interconnection maps. Basically, they are letting developers and users know where are the best locations for deploying, for interconnecting DG. So they are providing recommendations, perhaps indirectly, in some cases directly, to developers regarding, okay, this is where it's more convenient from a utility perspective to interconnect a plant. If you decide to go to this other feeder maybe, or this other substation, this asset may be reaching its hosting capacity, so there may be a need to reinforce the grid further, and that may imply investments that may need to be absorbed by the developer. So we don't recommend you to go there. Go to this other area of my service territory. So it may be indirectly, but basically this information is useful. It's like implementing a preventive mitigation measure. So this is making utilities more proactive in that regard. So the distribution resources plan, again, returning to California, it's an important initiative that is related, it's closely related to what I mentioned before, the DRP, using distributed resources as part of the standard portfolio of investment projects that the utility may consider for to address capacity needs and so on. So I provided also a link here with information if you're interested in learning more about the DRP. Okay, so in summary, we are experiencing a rapidly changing utility environment. So the utility landscape, the electric utility industry is changing rapidly. There are so many different initiatives, so many different trends. So it is very important to define a grid modernization strategy, a utility of the future strategy. And that strategy needs to address some of these key aspects that we discussed. So the proposal here is that this strategy needs to be holistic. It needs to look at infrastructure aspects. It needs to look at business. It needs to look at regulatory aspects as well. So this is a potential framework because the point here is that usually when we discuss utility of the future or grid of the future, we focus on the grid itself, and we propose general solutions that may not apply to all markets, may not apply to all realities. So instead, what we decided to do here is to propose a framework that can be adapted to different realities. So let me go through this framework real quick. So we have a foundational layer, that's how we call it, this one here. That foundational layer looks at, okay, the basic needs of a utility system, the foundational infrastructure and resources. So before, to give you an example, before thinking about adding intelligence to a grid, we need to make sure that that grid is robust enough. For instance, that aging assets are being replaced, that the grid is maintained properly. Besides that, that the utility has the resources that it needs to operate the grid, because on the resources side, utility engineers, utility executives, there is also an evolution there. Basically, what we are seeing is a more multidisciplinary profile for utility colleagues. That's an emerging need. We also need to look at standards. We also need to look at models, computational models. Now, it's paramount to have accurate and robust computational models, not only of transmission grids, but also distribution grids. There are utilities that are even developing models of secondary grids, low voltage grids. And there is a lot of interest on having consolidated models, since now what happens in distribution, the volatility, the dynamic behavior of distribution systems, they are becoming dynamic now, may affect also the transmission grid. There is interest in developing joint models that consider the entire T&D system. So we need to have those models too. We already mentioned business and regulatory aspects. We talked about it already. Then we have organizational and processes aspects as well. So the utility organization, as we know it traditionally, needs to evolve to address this new reality. On top of that, once we have addressed that, those foundational aspects, then yes, we need to get into what we call the enabling layer. We need to add incremental intelligence. We need to add enabling infrastructure. Enabling infrastructure could be, for instance, a robust communication system. To give you an example, if we if we want to operate and monitor in real time, we need to have a communication systems that allow us to do that. Then we have the application layer. Once we have all the infrastructure aspects covered, then we need to develop robust applications that allow us to process all that data that is being captured and that allow us to interact with the customer in real time. So we need a lot of analytics. And this is going to continue an evolving field. So it's very important to keep track of innovations. It's very important to take the lead. For utilities, it's very important in this evolving environment to try to be ahead of the curve. So the innovation layer calls for R&D aspects, for implementation of pilot and demonstration projects to be able to learn. So we believe that this is a holistic approach to the utility and grid of the future. And certainly there are feedback loops. There needs to be communication between the organizations responsible for each one of these initiatives. And this needs to be holistic again. Okay, so I have just an example here before I finish the presentation. And this by no means I'm saying that this is what is going to happen. This is just let's see, for the sake of discussion, this is just something, a potential scenario, a potential reality, something that may happen in modern and future distribution grids. So, you know, this is the traditional grid. Basically, we have a distribution feeder, a very simplified distribution feeder here with substation, a distribution substation, a distribution transformer, and then we have several service transformers. We have a normally open tie and neighbor feeders. It's a very simplified model. So this has been traditionally what we have seen in the distribution grid. More recently, this is what we have seen. We have seen proliferation of distributed generation, right? So now we have distributed generation that is connected directly to the substation. We have some distributed generation connected directly to distribution feeders. And then we have some behind the meter distributed generation, right? So, well, this would be, for instance, a distributed generation connected to a secondary system, or and this would be potentially distributed generation, behind the meter distributed generation. So let's suppose for a moment that you have heard about the microgrid and nanogrid concepts. So let's suppose for a moment that we have the technology, and let's suppose for a moment that these generators or resources in general are firm. So we are able to implement single customer microgrids or nanogrids. Let's call them nanogrids, okay? So basically what that means is that if for some reason I lose the rest of the system, I am able to self-supply. So this is related to what I mentioned before, grid defection and load defection. I may be still connected to the utility grid, but I may be able to produce cover most of my energy needs. So that could be a potential scenario, right? So now let's suppose that, well, we have many of those, and we say, well, you know, actually I can go beyond that. I can go beyond supplying, self-supplying. I could supply, for instance, part of the load of my neighbors. So that could be a secondary system microgrid, right? Another one could be, okay, I have enough distributed resources that I can supply part of a feeder. So that could be a partial feeder microgrid, for instance. And then somebody may say, well, actually, I can have enough resources to supply an entire feeder if there is a contingency, if there is an issue in the sub-transmission or transmission grid. Or even during a normal operation, I could develop a local control area, basically. I could have that control technology and implement it. And then somebody may say, well, I could have a full substation microgrid. And somebody may say, well, actually at the end what we're going to have is an interconnected set of microgrids. Is that the future? Well, who knows, right? What I'm trying to say is that these concepts, the technology for implementing these concepts is becoming a reality. Now, in order to implement some of these interesting ideas it's necessary also to address the regulatory and business side, and we are not there yet. So in this specific scenario, the one that we are seeing right now, we need to address ownership issues. We need to address also, well, transaction issues. Who is going to pay for electricity in this case? Who is going to be responsible for operating the grid? Liability issues, etc. So that side, there is plenty of discussion about it, but that side is lagging, I would say, with respect to the grid, the technology side. So the point of this presentation is, you know, we must not forget about that aspect. We need to take care of the business and regulatory side. It needs to be done at the same pace or even at a faster pace than what we are doing on the technology and grid side. I believe that finishes my part of the presentation. So I think that Saeed is going to talk about now about the next generation network. So thank you, and I'm going to be open for questions in a moment.
Thank you so much, Julio. I'm going to go ahead and move the ball over to Saeed.
Right. Thank you very much, Julio. Great presentation. I just wanted to encourage everyone to submit your questions through the chat box to me. And basically, when you see the list of participants, you can just right-click on a person, and then there's the option to open the chat box and type your question as we're talking. And just as a reminder also, this presentation, the webinar also will be posted. It's being recorded, and it will be posted on CIGRE NGN website. And we do also have some of our past presentation there. Basically, that is, the address is CIGRE-USNC.tamu.edu/NGN, or you can just always Google CIGRE USNGN, and that will be your first search result. But now with that, I just wanted to talk to you about the CIGRE NGN. Here, Ashley, if you could just let me know, how can I proceed with the slides here?
In the very top of your screen, you'll see the number 29, and you'll see an arrow. Go ahead and click on the gray arrow to the right to advance.
Okay.
In worst case, I can do it for you.
Oh,
there you go. You got it.
Okay, perfect. So basically, let's see that if the, yeah, I guess that this is the first one. What is next generation network, or NGN? That the CIGRE US NGN basically established for early career professionals with less than 10 years of experience and students in power industry. CIGRE US NGN membership is free for students, and young professionals also receive 50% discount for up to 2 years. The NGN basically seeks to facilitate a successful transition into the power system industry by providing resources and networking opportunities. And you can just go to the link, and there are all some more detailed information about our membership here. Basically, these are the few opportunities, or samples of the few opportunities that you receive as you join CIGRE NGN. That would include participation in educational and professional webinars and tutorials. You can attend CIGRE conferences. One recent activity that we started last year is a paper competition, which has been very well received. We had several prizes for top presenters, including a trip to Paris to attend CIGRE General Session, and also Grid of the Future Symposium. And I do encourage you to participate in this great program. And this year, we just finished that program, and the presenters, basically the select presenters, will present their papers in CIGRE Grid of the Future upcoming conference, which I will talk about that. But usually we start around June, July timeframe. We send out the call for papers, and that's where you can participate in the program. Also, another thing I want to mention, as an NGN member, you also get an opportunity to get involved in CIGRE technical working groups. Okay. So these are basically the people. We have right now 14 individuals that are currently running NGN's executive committee. Our chair, Jessica Lau, and the rest, the names, you see that we put a lot of effort to support our members and also expand our activities. Just in last, I want to encourage you and invite you to join us next month in Philadelphia for 2016 CIGRE Grid of the Future Symposium. You can find more information and register at CIGRE USNC webpage through the link that you see on the script. And you also have the opportunity to meet several of us. The NGN US committee member will be there, so we will be glad to talk to you and basically provide you with more networking opportunities at the symposium. So with that, I want to thank you again, but I want to now move to the Q&A portion of the presentation. So I received a few questions here, and I will go through that, but feel free to keep posting your questions. So Julio, the first question I have for you is that basically you mentioned some of the concerns on DG integration for the utilities. What are the typical studies that needs to be performed to ensure that safe interconnection of the DGs for the utilities and not having any basically adverse impact on the system?
Sure. Yes. Yes, I'll be glad to talk about that. Well, it depends. I would say that it varies. It depends on the. There is an increasing complexity in those studies. It depends. It's a function. This is a function of the size of the DG technology, the type of the DG technology that is being considered for interconnection, the existing penetration levels of DG, and also the location where the DG is planned to be interconnected. So there are a series of different studies. The simplest ones would be what is called screening studies. Basically, a screening study is basically a set of rules, a set of tests that are performed that generally are fairly quick, fairly simple. That provides a quick estimate for utilities of the potential impacts and the severity of those impacts. So usually when one of these screening tests is performed, if the DG application passes the screening test, then the expectation is that there are not going to be significant impacts. If it doesn't pass the screening test, then this depends, of course, on every state's regulation, every regulation under which a utility operates. But if it doesn't pass the screening test, then there may be the need for an additional study. An additional study could focus only on the steady-state aspects. Basically, you just have to run a power flow under a series of scenarios, and those scenarios may consider different loading conditions and different DG output conditions. Then the next step would be also consider the dynamics, not only the steady-state aspects, but also the dynamic aspects. And that would be, for instance, if we are talking about a variable distributed generation technology like photovoltaics. Okay, let's study what happens when we have a DG output fluctuation. For instance, in a cloudy day, the output from a DG plant may fluctuate significantly. So let's study how that affects voltage fluctations, how that potentially create undesired interaction effects with voltage regulation equipment, with capacitor banks that are being controlled by voltage. And another aspect that may be of interest is let's analyze potential interactions with protection systems, overcurrent protection systems, for instance, in distribution. If the DG technology, for instance, if it's a synchronous generator technology, well, it will contribute with short circuit currents, and that will affect the utility protection system. So let's study that. And then you can get into even more advanced studies. Some of those advanced studies may consider stability. They may consider even transient analysis, harmonic power quality analysis. Generally, most of the studies focus on steady state and dynamic aspects. There are specialized studies, but usually those are performed in systems that already have high penetration of DG, and in systems that are considered weak. Let me use the word weak here. What that means is to give an example, a system that has a large equivalent Thevenin impedance. So a good example would be a long rural feeder. Let's suppose that we have a feeder that is 50 miles long, that is lightly loaded, and I want to connect a plant, a large PV plant at the end of that feeder. So that feeder is not stiff. The opposite of weak would be stiff. What that means is that there is a large interconnection, equivalent interconnection impedance at the point of interconnection that may accentuate the potential impacts caused by the PV plant. If we interconnect that PV plant at the beginning of the feeder, or directly to the substation, or directly to a sub-transmission or transmission system, it's very likely that those systems are very stiff. They behave almost like an infinite bus, at least from the point of view of that PV plant. So impacts are going to be minimal. So those are some of the considerations. Those are some of the studies.
Right, great answer. So the next question is basically, where do you see more increase of battery energy storage systems, distributed and behind the meter application, or large and utility scale installations? And I guess my kind of follow-up question on that would be also if you could talk on the application of each of those renewables, basically reliability purposes, or anything you can add to that.
Okay, well, that's a great question. I would say that probably both. I think that both are receiving plenty of attention. Certainly, utility scale systems are receiving a lot of attention lately because of some of the mandates that I mentioned before. But even in the case of California, when you look at the specifics of the mandate, it includes a percentage of the total installed capacity is going to be utility scale storage systems, and another percentage is going to be behind the meter energy storage systems. So I think that both are growing. Probably, yes, utility scale systems have been the more traditional application, but lately, especially in the last year or a couple of years, we have seen new products that we were not expecting that they were going to be released in the market. Perhaps the most popular one is Tesla's Powerwall. So that's a behind the meter battery energy storage system. We also have Sonnen, the German company, Sonnen Battery, that is releasing new products too. So there is plenty of activity in the behind-the-meter market. And especially because, well, I mentioned before, the possibility of self-supplying, the ability that a battery energy storage system has of mitigating some of the potential impacts associated with interconnection of photovoltaics. Basically, if you have a combination of both, you can consider the combination of PV plus battery systems as firm generation. So that enables other applications. I think that covers the first part of your question. The second part of your question, could you please repeat it, S.A.?
Basically, you did respond on some of those, but I was asking on the application of basically either of those different type of implementation. Sure.
Yes, and yes, the applications vary. In utility scale systems, especially if we are talking about, let's see, transmission applications, then you can get into some of the applications that are related with market participation, such as frequency regulation. You could even talk about energy arbitrage. In the case of behind the meter, I would say that probably what some end users are looking at is, as I mentioned before, the possibility of, okay, I have energy storage and I have PVs, or only, let's suppose that I only have energy storage. Well, that increases the resiliency of my own nano system. So if there is an outage, if there is a reliability issue in the distribution grid or transmission grid, I'll be able to self-supply I'll be able to be independent, at least for a few hours. Now, some utilities are proposing the deployment of behind-the-meter resources. Green Mountain Power is one of those, and part of that proposal is to control those behind-the-meter resources to do things such as peak shading, right? So to be able to defer capacity investments. So that's another potential application. So I would say that it varies, but generally transmission applications are more related with, utility scale applications are more related with some of the market participation applications that I mentioned before. More recently, there are some distribution applications too. One of the innovators in this space was AEP. AEP has explored the utilization of battery energy storage systems for instance, for peak shaving, for intentional islanding during outage conditions. There is a very famous application in West Virginia, Bowles Gap. Basically, what they did was to deploy a battery energy storage system in a rural theater, and they have been using it for during contingency conditions. Microgrids is another application. In microgrids, basically, you can have a combination of different distributed resources, and if you have, especially if you have renewables, then you may need battery systems to compensate for the volatility of those renewable resources. So it's a rapidly growing field. I would expect plenty of additional activity in the next 10 years.
Okay, great. So we are already at top of the hour, but I just wanted to ask you one last question here, if you could just briefly answer that. In the example that you showed on the multi-microgrid and nanogrids being connected to the system, will there be also communication between the microgrids, and basically who controls all this microgrid?
Oh, yeah, that's a very good question. Yes, I mean, in order to implement this concept, I think that I mentioned that in the presentation, you need a robust communication system, and that's a big problem right now. So let's see. So if we had fiber everywhere, that would be great. You could do many of the things that we are discussing. The problem is that we don't have fiber, right? We have other technologies, and we have limitations. We have latency limitations, bandwidth limitations. So yes, you need to address the communication side. But let's suppose for a moment that that problem is solved, okay, the communications side. Well, there are still control aspects, so in operations aspects. So in that specific case, so okay, a good question is, how am I going to disconnect? Let's suppose that I'm allowing intentional islanding. How am I going to disconnect from the grid and reconnect, synchronize again to the grid? How is that process going to look like? How should I address safety concerns? I'm going to have a utility crews operating the grid and maintaining the grid, and how am I going to address those safety aspects? That's an additional question. And on the control side, also, well, how am I going to control voltage? How am I going to control frequency when I'm operating in islanded mode? Voltage, for instance, when I'm operating in interconnected mode, who is going to control what? What is the let's see, the most recommendable ball-bar control scheme? So there are many questions that need to be answered once the communication aspects are solved. So who is going to operate the grid? That's a very good one. Is the utility, probably the utility or the grid operator. If there is a grid operator figure, well, most likely the grid operator would be the one controlling or operating the grid. But if that is the case, then we need to answer one of the questions that I mentioned before. Okay, ownership, liability, to what level of control? What level of control are we referring to? Are we talking about dispatching these resources? Are we talking about just monitoring these resources? So it's like Pandora's box. I mean, there are so many questions that we still need to answer.
Okay, that's great, and thanks again for the presentation and answering the question and discussions. With that, Ashley, just give it back to you.
Very good. Thank you, everybody, for attending. I appreciate everyone staying on the line to the very end. The presentations will be available, as Saeed said, at a later date as soon as we post them. And have a wonderful rest of your day.
Thank you, everyone. Thank you for attending. And thank you for the invitation, Saeed. Thank you, Ashley.
Thank you, Julio. Thanks, everyone. Have a great day.
Bye.
Have a great day. I'm going to go ahead and close the line now. Take care now.